So, we are on to 15th lecture, and we were discussing pre-treatment of hot metal, and I think when I last finished the lecture, I was talking about desulphurization, external desulphurization or desulphurization pre-treatment, which is between blast furnace iron making as well and steel making. So, we continue with our discussion on external desulphurization, and I think in the last class I was talking about desulphurization thermodynamics, and I had drawn a graph just to show that the temperature does not have much influence on the sulfide capacity, for which the definition also I have introduced. And this was, I did not label the excess, and this is percentage Al2O3 alumina in slag. And I have drawn two curves, and I said that one curve is something like 1600 degrees centigrade, and the other curve is about 1500 degrees centigrade. Okay? And this is in a basic slag, and this is with increasing percentages. So, it essentially tells us that I have indicated that the temperature does not have too much of an influence on the sulfide capacity because of the equilibrium constant, which is not a very strong function. So, it does, however, shows an increasing trend that if you increase the some temperature, the sulfide capacity of the slag increases, but the sulfide capacity of the slag decreases with percentage of alumina. So, this axis I think I forgot to label during my last lecture, and you may just make that amendment in your notes. And this figure was introduced in order to show you basically the role of increasing temperature on the sulfide capacity of the slag. So, I finished my discussion on the thermodynamic part. I introduced a definition of sulfide capacity, and I have also shown that what is the meaning of L sub S, which we call as a sulfur partition coefficient, weight percentage sulfur in slag divided by weight percentage of sulfur in metal. And for that also I have written an expression, and where I have shown that sulfide capacity as well as the activity coefficient of sulfur in the metal and activity coefficient of sulfide in the slag, these are the factors which will enhance the value of LS, and on the other hand the oxygen potential of the metal will have a completely opposite influence on the partition coefficient. That means more is the dissolved oxygen in metal, you will have lesser value of partition coefficient. That means it will be difficult to remove sulfur or take sulfur from slag to metal, and that's the reason why I say that steel making is not a favorable site for removing of sulfur, because at any instant of time during steel making you will have considerable amount of oxygen that is dissolved in molten metal. Okay? Could be 500 ppm, 400 ppm or even more. Now, in the context of writing the desulphurization reaction, I have written the molecular form also and the ionic form, and I have represented the equation in terms of a lime containing slag is there, the melt contains carbon as in hot metal, and then I have written the equation like calcium sulfide which goes to the slag, and we have carbon monoxide, and then so this is, and I indicated that if you write this equation, then temperature does not have a very significant effect on the desulphurization reaction thermodynamically, okay? But we will see basically this is a weakly exothermic reaction. So, I would say that desulphurization should be favored at relatively low temperature, but I have also made that statement that in fact when you increase temperature we always note that desulphurization, more sulfur gets transferred to the slag phase. That means this reaction is favored. And that is precisely, I have also mentioned that in my last lecture, that is precisely because of the kinetic factors, and that will come out now when I will talk about the kinetics of the desulfurization reaction. So, we have the slag metal, this is a slag metal reaction, and let us quickly go through our kinetics, metallurgical kinetics fundamental. So, this is our slag metal interface, and it is at this particular site that this particular reaction or desulfurization reaction will take place. And as we see here that we have species like calcium oxide which is there in the slag phase. So, this is slag, and then we have metal. And the reaction site is at the interface, and we have, for example, I would say that there is as far as the theory goes, there is a slag phase boundary layer, and also there is a metal phase boundary layer. That is what is the typical scenario, as when we postulate the mass transfer. So, basically this essentially tells us that sulfur which is there, it has to move through the boundary layer and reach here. Okay. So, transport across the boundary layer. Similarly, calcium oxide which is there in the slag phase. So, the slag contains calcium oxide, metal contains iron sulfide. So, here we have, for example, sulfur is there, and so here we have calcium oxide which is there. And similarly, from the slag, calcium oxide is transported to the interface, and also if you assume that carbon is there everywhere, the transport of carbon should also be there, and then we have the reaction between calcium oxide, or we can say the transport from an ionic form, we can say that transport of sulfur and transport of oxygen and ion, that is equivalent to calcium oxide transport. They come together, and then they reach at the interface, and then where this particular reaction then proceeds. So, if you stop this one of the transport process across the boundary layer, this reaction will not take place. So, all these steps, transport of sulfur to the reaction site, transport of calcium oxide to the reaction site, then the chemical reaction, and the movement of the product in the opposite direction, these are all kinetic steps which are connected in series. If you stop one of them, they will not come. The reaction will or desulfurization will not be possible. Now, we know from our kinetic fundamentals that essentially for most of the reactions, barring a few, at high temperature, because this reaction we are talking about is taking place in a blast furnace or in steel making or during the pretreatment. So, the temperature is something like 1300, 1400 or even 1600 degrees centigrade if you go to steel making. So, therefore, it is a high temperature operation, and high temperature the rate of the chemical reaction is very high. You should now isolate the desulfurization process into absolute chemical reaction, which is rearrangement, which essentially implies that rearrangement of bond etc. takes place. Sulfur is taken up by calcium and oxygen is taken up by Fe, and then carbon takes away that oxygen, and as a result of which this combination of product is formed. So, rearrangement of the bond is taking place at the interface, but that is preceded by many transport steps, and one of those is the melt phase transport across the boundary layer and the slag phase. So, this is the slag phase boundary layer, and this is the melt phase boundary layer. Okay. Now, typically it has been experimentally proved also that of all these steps, the slowest step is the transport of sulfur from the edge of the boundary layer to the surface. So, this is the concentration that what drives. So, if you consider that the boundary layer transport of sulfur controls the rate of the desulfurization process, so therefore, it is understood that this chemical reaction can be taken to be at equilibrium, because the rate of the chemical reaction is going to be, all other steps would be very fast. So, I would say that this calcium oxide concentration will be immediately prevalent right at the interface itself, because this transport has been assumed to be not rate limiting. Similarly, the chemical reaction which takes place at the interface will be considered to be very fast, and as a result of which we can say that this chemical reaction is virtually at equilibrium. So, there is an equilibrium concentration here, which may be concentration of sulfur, which may be close to 0. Okay. So, the sulfur, which I would say is equilibrium, and there is a sulfur concentration okay, C sub S equilibrium, and there is a C sub S which is the same concentration as the bulk, because as I said that the bulk is well starred. So, there is no difference in concentration. So, there is no driving force for transport. Essentially whatever is the concentration is the same concentration, and this concentration is represented as Cs sub bulk. So, that is the driving force for the sulfur transport in the whole case. Now, if you write down the mass transfer equation, for example, the rate of transport, that is equal to a mass transfer coefficient into interface area, and then I would say that it is the concentration of sulfur at the edge of the boundary layer, okay, minus the concentration of sulfur, and which is the equilibrium, which is the interfacial concentration basically. This concentration is fixed because I have assumed the reaction to be equilibrium. This is an idealization. This concentration is changing as a function of time. And if you now consider, if you can write that, and these units are all kg per second. So, this is kg per meter cube, and this is mass transfer coefficient meters per second, this is meter square. So, this becomes kg per second. So, that is the unit, and we can also write that it is, if V is the volume of the melt phase, and then we can say that dCs, and do not confuse this Cs with the sulphide capacity. This is the concentration of sulfur, third bracket essentially indicates in the melt phase, and I have also double, to make it doubly sure, I have represented the bulk concentration of sulfur, which is changing, and this sulfur is going to be preceded by a negative sign because there is a decrease, and then we can say that this is equal to Km into A into Cs star, Csb minus Cs equilibrium. Mass transfer is a first order process, and that is exhibited that the rate is proportional to concentration raised to the power 1, okay? And this V is the volume of the melt phase, and the kinetic equation is represented. So, this is the kinetics of kinetic equation representing the transport, rate of transport of sulfur across the boundary layer, which is essentially equivalent to the rate of the desulphurization process, because all remaining steps have been taken to be operating close to equilibrium. It is their idealization, they are not at equilibrium in reality. They do have certain finite rates, but in the kind of assumption that we make to make our life simple and to perform the calculations very quickly, we assume that one single step controls the rate, and remaining others are virtually at equilibrium. So, if you integrate this, okay, then we will find out that this integral basically, and if you apply the initial condition, because this is a first order equation, so we require to explicitly, we will result a constant of integration, and that constant of integration will be given by the initial condition, and which we say that at t is equal to 0, the Cs, okay, bulk is equal to Cs initial. The bulk concentration is changing as a function of time as more and more sulfur is going from bottom melt phase to the, and if we do this, then we have the final rate equation, and it tells us that this is going to be Csb minus Cs equilibrium, and then we have Csi minus Cs equilibrium is equal to exponential minus Kt, where this K is nothing but K mass transfer coefficient area by volume, which has a dimension of 1/2. So, this is the rate constant of the desulphurization process, and it is understood that at very large time, if the time is very large, then this term is going to be equal to 0. So, therefore, the bulk concentration will approach to the equilibrium concentration, which will be, if one calculates the equilibrium by putting in the delta G naught value for this, one can find out that the interfacial concentration of sulfur at the at the interface, because whatever sulfur is transported here, it is immediately converted to sulphide, and which goes to the as sulfur ion as what I have written here, then the sulfur from here will go to the S2, and then oxygen is going to come here. So, that is the way the products are going to move from the from the interface. So, virtually whatever sulfur reaches here, immediately that sulfur is going to be converted to sulfide ion. So, we will come out to be a very small concentration of sulfur right at the interface itself, and that is what. But nonetheless, if time is very, very large, as time tends to 0, infinity, okay, time tends to infinity, this exponential term will tend to 0, and as a result of which the numerator will tend to 0, which essentially will tell us that we should be able to get a very low sulfur concentration at very large amount of time. Now, this Km is the melt phase mass transfer coefficient. So, we will require a good amount of studying in order to have, for higher rate constant value, for high rate of sulfur transfer, we require a higher mass transfer coefficient. So, the volume is almost fixed because the reactor size is fixed, but these are process parameters. When I will be doing in the industry, when desulphurization will be done in it, either in a torpedo car or in a ladle, that ladle volumes are not going to change. So, that is not a process parameter, that is operating condition, and that is a fixed condition. But these are processing parameters, the interfacial concentration A and the mass transfer coefficient. This we can increase or decrease by carrying out the process under certain conditions. So, for a large rate constant, it is imperative that we will require a very large mass transfer coefficient and very large A, and that is embedded in the desulphurization process, which I will discuss when I will say the technique of desulphurization. In the desulphurization process, what happens? I have told you that we use 80% of CaO and 20% Mg, or sometimes 80% CaO and 15% Mg and 5% calcium fluoride as a conditioning agent. Now, these are injected into the melt. So, if you are doing desulphurization in the ladle, there are of course various processes. The KR process has a propeller driven stirring system. And why we want to stir the melt? Because we want to have a large mass transfer coefficient. The mass transfer coefficient, if you consider our fundamentals, that the mass transfer coefficient, when you do take a basic convective mass transfer coefficient, we say that mass transfer coefficient is a function of characteristic length, is a function of characteristic velocity, is a function of fluid viscosity, density, diffusivity. Okay? So, this is enough, I think 6 variables, and we have and there comes the characteristic velocity. So, and that manifests as the Reynolds number, okay? And we know that as the velocity increases, the mass transfer coefficient increases, because the boundary layer thickness is going to be smaller and smaller. The resistance to flow is going to, resistance to mass transfer is going to be smaller and smaller the moment we increase stirring. So, therefore, no desulphurization operation is going to be carried out without any stirring, and the KR process, which is very popular in the industry for external desulphurization, uses a propeller star. There is a design of, if you look at the cross section, so that looks like in a star shape. From the top, the propeller looks something like this. So, if that is the design of, I have not been, my drawing is not that good. So, this is the way the propeller looks like, okay, and it is a refractory, this height propeller, and it has this change kind of a, so because when the propeller rotates, the fluid wants to be rotated, so you have to create the maximum surface area, and this provides very large surface area, and then the kinetic energy of the propeller can be very easily transported to the melt phase, and it can impart a good amount of motion. So, this is the top view of the propeller. So, we start this vigorously. We do not use here, gas stirring is not very effective, because if you do gas stirring, the gas stirring efficiency is much smaller than the propeller driven system for the same energy input rate. Okay? So, the cost of energy is important, because you will require some stirring energy. If you compare it with the same energy input rate, you will find that this is going to be the propeller stirred or impeller stirred system is going to be far more agitated than a gas stirred system, and that is why the KR process of external desulphurization is very, very popular. So, when you stir it vigorously, then what happens is that we get a very large velocity, and that expedites the mass transfer coefficient. What about the area? Area is also a very important parameter. Now, we are adding various kinds of reagents, as I have indicated, calcium oxide, okay, magnesium, solid magnesium powders. So, these are going to be injected into the system. The moment you inject, then what happens is that we have an expeditious dissolution as well as chemical reaction, because the simple fact that you are injecting in a fine particle shape. Okay. So, we have calcium oxide, it is now available. I have drawn the slag metal interface in an exaggerated way here, but if large number of droplets of calcium oxide particles are injected, that indicates that there is an enormous surface area created where calcium oxide and FeS will come in contact with each other, and that is going to expedite the slag metal reactions. So, therefore, to get a very large interfacial area, this A is the reaction interface area. This is not the wall area of the vessel or the planar slag metal interfacial area. So, the moment you inject calcium oxide, the moment we inject MgA, huge amount of interfacial area is created, and that expedites the mass transfer rate, that leads to a very large rate constant value for a given system, and as a result of which high rate of desulphurization is going to be obtained. So, desulphurization will be done in ladle, or desulphurization can be done in torpedo vessels, which I have shown you in my last class. Okay. And whether you do it in ladle or whether you do it in torpedo, okay, you will have to have stirring, which is present here, and injection of powder, which also has to be there in the both system. They have their own inherent advantages. These are the shallow vessel. One single stirring may not be quite effective to produce good amount of stirring here, good amount of stirring. So, there is a region of intense stirring which is located close to the injection nozzle, on the other hand far away from the system. This could be little bit poorly starred, these regions could be not so well starred. This gives rise to, because of its adverse surface area to volume ratio, this actually gives rise to more temperature drop, because now this is of course an exothermic reaction. If you take Mg, which is in the gas phase, so the solid Mg you have injected, that Mg is going to be turning into liquid, and that liquid will instantaneously turn into gas, because the operating temperature is very at 1300 1400 degrees centigrade. Magnesium can be present only in the gaseous phase. So, this reaction is by far a very exothermic reaction, but that is not enough to compensate, because you are adding so much of solid reactants into it. Okay. The propeller itself is going to absorb some amount of heat. You have calcium oxide which is injected at room temperature, that needs to be heated up. So, the temperature drop in desulphurization, external desulphurization, is a must, if despite the fact that this reaction, okay, is MgS plus you have that is magnesium sulfide. This reaction being an exothermic, this is not enough to supplement the heat loss during the process itself, and little desulphurization accounts for a little more temperature drop than it is possible in the case of. But hydrodynamically, ladle desulphurization, this KR process, particularly the propeller used, is carried out in ladles, and ladle offers much more, it is a much more efficient system, and ladle also offers you to make it a gas stirred system, because the L by D ratio of ladle is far more favorable than the L by D ratio of this. So, this is a relatively poorly stirred system for the same amount of energy input. This is a better stirred system. This allows you, you can use in both the places, of course, gas stirring, and if you are using gas stirring, you can take advantage of the higher depth of the bath, because the potential energy of the gas is going to be gas you are supplying from the bottom. So, the potential energy input rate per unit mass of the liquid is going to be larger, because the potential energy of the gas bubble is dictated by the depth of liquid in the system, but the depth here is going to be much smaller. So, hydrodynamically this is more efficient, thermally this is more efficient. So, by many people, but this is a very large volume, ladles are not that big. So, you have the option to use both ladle as well as torpedo desulphurization vessel, and they are equally popular in the steel industries. Okay. So, I think I have given you enough idea about the thermodynamics and kinetics of external desulphurization, and these fundamentals are going to be useful when we study actually the steel making process. Now, I will not like to discuss this dephosphorization as far as pretreatment is concerned, because dephosphorization per se is only used in certain Japanese steel plant who are very highly concerned about. Sometimes what happens is they treat high phosphorus pig iron, and as a result of which there is an enormous phosphorus dissolved in the metal, and by doing in that case only the dephosphorization becomes very, very important. But that in India and in most of the countries, high phosphorus pig iron, which may be used down the road sometimes, but today at least not so popular. I think it is not contextual here to discuss dephosphorization. So I will say end my talk on lecture on pretreatment by saying that as far as the trend is concerned, most of the plants will be doing silicon control as well as sulfur control during pretreatment. Very few plants, there are few in Japan only, who do phosphorus removal through external dephosphorization, but we will talk about dephosphorization in the context of steel making in great detail, so that the fundamentals of dephosphorization, which is equally applicable to both pretreatment as well as steel making, will be known to you, and you can appreciate that if this phosphorization is done during pretreatment, how it is done, what is the thermodynamics, what is the kinetics of dephosphorization, and so on and so forth. But it is sufficient for us to note that as far as pretreatment of hot metal is concerned, we will be doing mostly silicon removal as well as sulfur removal. And as I have indicated, that we want to have a good adequate silicon in the hot metal such that it is sufficient to make the steel making process autogenous. Okay? We do not need excessive silicon, we do not need too less silicon. So, since blast furnace raceway temperature etc. fluctuates, raw material fluctuates, and if the blast furnace is not able to produce, the engineering is not so good, and it is not able to guarantee a fixed silicon on a daily basis, pretreatment will give us an option to remove silicon and thereby result in a hot metal which will have more or less a similar kind of a dissolved silicon, which is just enough to supplement the heat requirement of the steel making process. Sulfur removal is a must for us. If we are not able to maximize sulfur removal in blast furnace for some reason or other, in that case we have no option but to do external desulphurization. And in plants like JSW etc., there are standard desulphurization practices for hot metal. Every heat is subjected to desulphurization because of the simple fact that we are not able to maximize desulphurization in the blast furnace, and we know that in steel making, because steel making is an oxidizing environment, okay, despite having very high viscosity, steel making cannot give us adequate sulfur removal. So we are left with no option, okay, but to carry out external desulphurization prior to steel making particularly. And I think both of these, Durgapur steel plant at one point of time we had external desiliconization, and external desulphurization is very popular in many of the Tata plants as well as in integrated steel mills like JSW, as I have said. So with this I will close my discussion on external desulphurization, and I will move on to now the final topic of iron making, and that's the alternative iron making. So far what we have seen that the blast furnace, so the new topic is alternative iron making. There is a nice discussion that whether it is alternative iron making or it is complementary iron making. So I will, at the end of the discussion, you can yourself explore that where the definition really fits. Now, whether it is alternative or whether it is complementary iron making, so long what we have discussed is iron making through blast furnace. And we all know that blast furnace is the dominant iron production route, very efficient, and 90% of the liquid hot metal today is produced, more than 90% liquid hot metal is produced through blast furnace. All the steel, that 1.4 or 1.5 billion tons of steel that we produce, a bulk of that steel actually comes from blast furnace itself. Not 90%, of course. Okay. Now, the moment I say liquid hot metal, we must understand that iron is produced both in the solid state as well as in the liquid state. Indeed, when I was talking about the historical development, I have told you that initially mankind was not in a position to produce very high temperature. So, the primitive people produced predominantly iron in solid state, and then some kind of a refining used to be done mechanically or so, removing the slag particle, etc. So, those were basically not steel, but iron, and it is only in the last 200 years that the liquid iron production has become popular because of many inventions or innovations in the field of technology. So, today also iron is produced, good chunk of iron is produced in the solid state and as well as in the liquid state, and as I said that in the liquid state 90% of, we will examine that what are the processes actually in the solid state as well as in liquid state. So, other than blast furnace, iron is also produced in liquid state by other different processes, and parallelly iron is also produced in the solid state. So, therefore, blast furnace is just one of the routes, and I would say the major routes of iron production. On the other hand, in addition to blast furnace, we will see there are many iron making routes processes adopted throughout the world, some of them producing solid iron and some of them producing liquid iron. And it is those techniques which we want to address now under alternative iron making or complementary iron making. Before that, we must know that when you have such an efficient reactor like blast furnace which can produce hot metal very economically, what is the necessity of having a set of alternative iron making? That motivation must be clear to us. And the motivation for having alternative iron making are twofolds. One is that that the biggest disadvantage of blast furnace iron making is that it is heavily dependent on metallurgical grade coal because it needs coke, and we know that metallurgical grade coals are very rare, they are depleting at a fast rate, they are very expensive too. Of all the reagents that you use in iron making and steel making, in terms of iron ore, limestone, coke, oxygen, etc., the most expensive on a per ton basis is coke, and that coke is decreasing, the grade of coke is diminishing. It is getting, because in India, as I have indicated in one of the lectures, that we get coke which contains 25% ash. And what is that ash? Bulk of it is silica actually, and that is what is the blast furnace gets very high silica content because we are using Indian coke, and that is why what people do, that to contain the silica content so that blast furnace can be operated at a little bit of higher temperature, okay, coke blending is done. So, we buy coke from Australia, we buy coke from South Africa, blend them together with Indian mixture, and if we blend them with 1:1 weight fractions, in that case we will see Indian coke which contains 25%, on the other hand imported coke 7 and 8% ash will give us a coke which will be about 13-14% or even 11% of ash, which will be significantly better than using the Indian coke alone. Now, coming back to that point, so the grade of coke is going down, the coke price is increasing on a day by day basis, and coke is getting scarce, okay, because the metallurgical grade of coal required to make coke is depleting at an alarming rate. So, the search for an alternative fuel, and we know that coal cannot be charged in massive or giant metallurgical or iron making blast furnaces because it does not fulfill the requirements of strength with good reactivity, etc. And therefore, we have to alternative iron making. That means that if you want to replace blast furnace, the objective would be that that process has to be coal based rather than coke based, because blast furnace is heavily reliant on metallurgical grade of coke. So, that is one particular driving force or motivation for going to an alternative iron making process, which will use a low grade fuel, not metallurgical coke, not use the metallurgical grade of coal or coking coals, okay, but can just take any other variety of coal with some lesser sulfur content, lesser silica content, and that can be used to produce the reducing gas or the ensured reducing environment, and the whole process also generate necessary heat to supplement or to run the process. On top of that, we will have, we know that in steel making enormous amount of heat is released. For example, carbon and silicon, and as I said, that silicon control sometimes is not so perfect. So, at some point of time when you start blowing oxygen, even though the silicon and carbon oxidize, a significant amount of iron also gets oxidized, okay? And that is why, while the blast furnace slag will not contain 1 weight percentage of FeO, we will see that the steel making slag will contain 20-21% from 15 onwards, 15% and above FeO content in the slag, because a significant part of FeO, if it gets iron, dissolved iron gets oxidized, and the oxidation of dissolved iron, Fe plus oxygen is equal to FeO, is an exothermic reaction. So, that also increases the temperature. So, in steel making, more often we require coolant, okay, that if the temperature goes too high, because we need oxygen, we have to pump in oxygen into the steel making reactor in order to remove phosphorus, in order to remove carbon, in order to remove silicon. But if we find that the temperature is increased, then what happens is the plant as such generates a lot of scrap, steel scrap. Those steel scrap at room temperature are charged maybe 3 tons, 2 tons, 5 tons, okay, in order to get the temperature in the reactor down. But as the processes in plants have become much more efficient, and the yield of iron has been continuously increasing, there is a huge scarcity of scrap now, because almost all the iron that comes from blast furnace, all means about 95%, 94%, they are converted to finished product and sold. So, you are left with no scrap, in-house scrap, which you can use as coolant in the steel making reactor should the temperature of the melt increase beyond a certain threshold during the steel making or oxygen blowing process. As a result of that, to circumvent the problem that we do not have indigenous scrap or in-house scrap available, so what can you do if you have to cool? And the solid state iron that we produce through as a part of the alternative reaction, iron making processes, those solid irons which we call as DRIs, direct reduced irons, which are basically sponge iron. And the name sponge iron comes because if you look under microscope, these are partially reduced. So, you take hematite ore, for example, and if you use solid and then if you reduce it, I have also told you this in the context of my discussion on blast furnace, you can get a mixture of Fe, FeO. I am still writing here FeO for the sake of simplicity, and not 0.947, because now we are not doing stoichiometric calculations, okay, and we can have this a mixture of these, and which essentially tells us that some oxygen, some metallization has taken place, oxygen has left the matrix of iron ore, and as a result of which you will see that there are pores. It is like a exaggerated spongy structure, okay. So, if you it will not look like sponge, okay, but if you look at it under microscope, you will visibly see many porosities, okay, physical porosities, and it is because of the escape of oxygen, partial removal of oxygen from the iron ore itself, and that is why the solid iron produced by partial reduction of Fe2O3 or Fe3O4 is termed as the DRI, direct reduced iron or sponge iron, okay. So, these DRIs now can be used in the steel plant as a coolant, okay, because scraps are not available, and they can they are also quite a bit of metal is there in the ore. So, they are not like scrap. Scrap is far more pure, of course. Scrap will contain 99% iron, but in this case it is not going to be 99% iron, okay, but it is a better product than anything else. So, DRIs can be used as effective coolant in the absence of any scrap in the steel industries. So, these two reasons that coke is decreasing, we want a cokeless iron making process, and that we have no scrap available in the steel plants or very little scrap, we need coolants. So, there the DRIs particularly provide us an opportunity to use solid state iron, iron reduced through solid state as an effective coolant. Now, there are many routes given this objective, and that we want to produce liquid iron using coal and solid iron using coal. There are a host of processes which are available. So, I will just therefore summarize this saying that if you want to have alternative iron making, AIM, okay, alternative iron making, and then therefore we can say that they are solid state, and then the product of alternative iron making or iron can be in liquid state. Alternative iron making processes. Alternative iron making processes produces iron in the solid state. Okay? That is how you should read it, otherwise the arrows will not mean anything. Alternative iron making processes that produces iron in the liquid state. This alternative iron making processes, and as I have indicated, uses alternative source of fuel and reductant. As far as solid state iron production is concerned, there are two different types of reductants possible for us. One is gas based and the other is coal based. Gas based, for example, you can see you can have here natural gas, for example, and you can reform natural gases. So, for example, if you take methane, you can get carbon monoxide and hydrogen from methane by reforming of methane, and that we have seen that carbon monoxide is a very good reductant, hydrogen is even a better reductant. So, a mixture of hydrogen, will not melt iron, we do not require very high temperature here, we just want to facilitate reaction, and we have seen in the blast furnace that around 900 degrees centigrade or 1000 degrees centigrade in the straight reduction zone, the reduction of iron ore is complete. So, we are talking about a temperature of 1000 degree or 1100 degrees centigrade at the most, okay? And when we can use carbon monoxide or hydrogen, okay, and which can come out from natural gases, and there are now several processes there. Similarly, coal based processes are also several. One such process is the called rotary kiln or SL iron process. Gas based process, we have Midrex, we have HYD, and we have shaft. These are popular processes, there may be others, and we will not discuss everything, because I will, from each category I will take up one and then I will discuss. Then there SLRN process is there, and then we have, I think, other processes like this is fast met, and this is comet, I think. So, these are gas based and these are coal based. Okay. Similarly, if you go to liquid state reduction, and that liquid state reduction will give you Corex process, it will give you Finex process, then high smelt, and fast smelt. That is what it is. So, I think I have given you the right ones, yes. So, these are the various kinds of processes that are available today in the market, okay? And as far as the most popular processes are, Finex is getting momentum, some of the processes have just been commercialized. This is very popular in India, and Midrex is also popular. Okay? So, Midrex process, for example, will use some kind of a reformed natural gas and so, and that the technologies are different, but essentially these are all, they may be using different kinds of gases, they may have different kinds of geometries, reactor geometries, etc. This uses a coal based process, and this also Corex, which produces in liquid state, uses mostly predominantly coal or a mixture of coal and coke. Now, India, so the solid state, these products can be, I will say, gas based DRI, whatever this product is there. This I will call as a coal based DRI. Okay. Now, for example, if you look at the location of DRI making plants, so solid state essential, else sponge iron or DRI making plants. So, DRI India by far is the largest producer in the whole world, okay, that you should note. Okay. So, we have many DRI plants in the country, therefore, because we are the number one top producer. And the location of the DRI based plant will depend on the relative availability of the natural gas as well as coal. For example, if you want to set up a DRI plant close to in the eastern zone, that has to be not gas based but coal based, because of the simple fact that we have all the coal mines located in the eastern sector of the country. On the other hand, if you want to set up in the near Bombay or Gujarat a DRI process, in that case we can see that DRI making process has to be a gas based process, because natural gases etc. are available in abundance in the western coast. So, predominantly all the, and SR, that is why if you go to SR Steel, which of course is now I think Nippon ArcelorMittal Nippon Steel, A&M, and they have this Midrex process, because it does not make sense, because in Gujarat coal is not available, you have to transport that coal there, so you will incur additional expenses, but there could be pipeline that you can from the sea you can have directly gas pipeline conveying the natural gases, and you can thus obtain very easily or at an easy price, cheap price, the reductant as well as the fuel for the process itself. So, in the eastern region we can now know that we will have the mostly coal based plants, and there we are going to have west coast we will have only the gas based DRI plants. And as I said that I will discuss this from each of these category, 3 different processes, and I will start my discussion on SLRN process from the next class itself. Okay, so I will take one more lecture or maybe 1.5 lecture more to finish my discussion on all the 3 processes that I have listed under the alternative iron making process.